Why do we need activation functions? You probably know that many machine learning models, including large language models, uses activation function in each hidden layer. And what if I told you that without these activation functions, even a deep neural network becomes just a straight line? They are mostly used, as I mentioned, used in ML, machine learning models, deep learning in deep neural networks, and if every machine learning model uses this activation function in each layer. So even I can share my own experience that I use DNN to classify signal and background. That is part of my PhD thesis work. I'm using PP collision data to do physics analysis. There I also use activation functions. We will and we will understand this activation function in details, and we will build, not just we will learn the theory, we will build a neural network and compare the behavior of the model or the performance with and without activation functions, how it performs with the activation function and how it performs without an activation function. So to demonstrate this experiment, I have this set up the code, and I am using the Keras library to build the model to demonstrate for the demonstration purposes. And I'm taking a simple, as you probably know, an ML or ML is a function approximator. It can fit any function with multiple layers of with multiple hidden layers. So I'm generating x from minus 10 to 10 to 1000 20,000, and I'm taking sine function. I want to fit or train a DNN to fit a sine function, and I am adding noise here, random lentex, so that, as you probably know, real data is not that um, real data always have noise. So to be as realistic as possible, I am adding the noise, and here I am scaling the, as you probably, if you have trained a DNN model, scaling the input features to so that they have mean 0 and variance 1 helps the stochastic gradient descent. I can prepare a separate video if you want why we need to scale the input features. And here we are building a simple DNN model which takes the activation, and we have multiple layers. You can see the first input takes one, shape is one, and then we have a hidden layer with 64 nodes or neurons, and then we have another layer, 32 neurons, dense layer 16. Finally we have one output, that is y predict. And each layer, as you can see, we have activations, and we have three set of experiments. We want to check when the activation is none or there is no activation, how the model fits the sign and how the predicted looks like, y predicted, how it is it sign or whatever, we will check. Then we will use ReLU. This is the most popular one, which is also I use this activation function in my research while building model DNN model to train and to classify signal and background events. And then we have 10 hyperbolic activation functions. Here I can share the full code if you want. I will upload it on Git and share the link. And here I'm fitting for 3 cases. I'm fitting the model and doing the prediction, and this part I'm trying to plot to see to the result. Here I am plotting the noisy data. This is the true, and here I am plotting the function, the predicted one. And as you can see the result, I told you that I am taking x from -10 to 10 and y as taking the function as sine of x, and you can see the black one is the true, or the y is equal to sine x. And this is the noise, effect of noise. You see the balls, the circle one dotted, these are the noise, and the model is trained on this noise data. As you can see, the linear function, when there is no activation function, we end up fitting a straight line. And I will come to why we, even if you add multiple more layer or how many neuron you have, doesn't matter, you will end up fitting a straight line. And I will come to that. There is a theory, numerically you can demonstrate that or prove that without activation function your model will end up fitting a straight line. And then we have a ReLU activation function. As you can see, any nonlinear activation function that fits the model well. And this is the model summary. You can see, as I mentioned, we have dense layer 1, 2, 3 with 64 neurons and so on. Let's understand with a simple example why it ended up with fitting a straight line. So first, let's assume that we have multiple layers and each layer has one neuron. Then you can see the first layer, the output will be y is equal to wx plus b. If there is a activation function tan h, then the output will be tan of tan hyperbolic of wx plus b. So then we have a second layer. It takes the y and multiply with w2 weight plus b3 b2. Then third layer with the multiply with weight w2 and b3. As you see, if you do some rearrangement, and you will find that you can convert this equation to this form: y is equal to w prime. You can, w prime is this and w b prime is this. You can see you ended up with another straight line, y is equal to w prime x. This is also a straight line, as you can see. Similarly, here I took one simple example to demonstrate a simple example with one neuron in each layer. Similarly, you can try on adding more number of neuron in each layer. For example, multiple neurons. For example, for this case, you will also, after rearrangement, you will see that you will end up with a straight line. Explicit, I have one example, more example with two neurons. You can see, I'm not going in details, you can work it out. You will end up with again I am getting a straight line. So the key insight is the entire network will still reduces to a single linear function x if there is no activation function. If you want to learn more about what are the ReLU functional form, ReLU is simply f of x is maximum of 0 and x. That means I have here, this is the ReLU. If x is less than 0, then the f of x or ReLU y ReLU of x is 0, and if it is greater than 0 then it is just a straight line, and this is the tan hyperbolic form of this. Thanks for watching, and let me know if you want the slide. I will upload it on Git and share the link. And if you want, I can prepare one more video on why we scale the input features. Thanks you. Bye bye.